Hi, in this video we will find the volume of a solid of revolution when the region to be rotated is the region between the graphs of two positive functions. Okay, so here we are going to have two functions of positive and continuous. So let me say f and g on the interval a and b. The region between these two, so two functions, both of them are positive, then the region between these two we start rotating about x-axis. What will happen here is that when you rotate such a region, well, I need a little bit longer x-axis. Yes. When you start rotating such, let me see if I can do it completely here. Yes. When we start rotating, what you notice is that such an object will have a hole in between. So if I rotate this, will be of you see it is an object, and from the body we have taken out another piece. So it is like you have area of this guy here, volume of this guy, the solid rotated object about x-axis, but we subtracted from that this second solid object. Okay, so if you want to find the volume, so this will be volume of the bigger object, so it will be integral a to b of pi f of x, or the upper function squared dx, minus a to b pi g of x, the lower function squared dx. And if you put them together, you will see that there's one function, f of x squared minus g of x squared dx, integrate from a to b, and then multiplied by pi. Or, well, let me just write this version also, which always is helpful. Upper function squared minus lower function squared, integrate, and then multiply by pi. This is called a washer method. The reason that we call it washer method is that when you try to find a slice of this object, what you will find is not a complete disk. It will be a disk with a hollow hole in between, which is like the washer. So let me just sketch it here. So it will be a disk with a hollow in the middle. That's washer, yes. That's why this method is called washer method. Again, the problem is that we are rotating a region between the graphs of two positive functions. If it was only one function, that was just a regular one, and we saw that two ways of getting this is this gives us this formula, or equivalently this other formula here. Okay, let's see some examples for this. Okay. Oh, I will need more space definitely. Okay. A region enclosed by these objects. I always do sketching so that, well, sketch things helps us to understand better. Y equals to x squared. Well, it can go both sides, but the other one, y equals to x, is just one side. So we have on the region is on the interval 0 to 1, and between these two. Where did I get 1? Well, intersection of these two, x squared equals to x, gives us x either 0 or x is 1. That's the intersection points. Now, we start rotating this object, this region, okay? When we rotate, this time again, we get something like cone, but there is a hollow, there's a hole in between. Well, it doesn't go through, but it just gives you that feeling. Well, what is volume of that? It's pi integrate from 0 to 1 of upper function, which is y equal to x squared, upper function is squared, minus lower function, in this case is x squared is squared. So this is upper function squared. This guy is lower function squared, then dx. This will give us pi, and x squared, the antiderivative is x cubed over 3 minus x4 is x5 over 5. You go from 0 to 1. And that gives us pi 1 over 3 minus 1 over 5 minus pi times 0. Well, that will give us 15 minus, 5 minus 3, that's 2 pi over 15. That's the volume of this solid of revolution. Well, the same story will go for the rotation about y-axis. This time, the only difference is that everything will be written in terms of y, so the volume is going to be integral from a to b of, this time is the upper square minus lower square will turn to the right function squared, there's a pi outside, minus the left function squared. Everything in terms of y, and then dy. Okay, let's see this in an example. So here we have what is the region we have here? This is x squared plus 1, nice. This is this parabola. Y equal to 1. Did I do this one not nicely? Okay, so this is parabola. Y equal to 1. Oh, this is supposed to be x equal to 1. And this is x equal to 1. So the region is this guy here. Y equal to 1. And what would be the other point of intersection here? Well, x equal to 1, you plug in there, so y equals to 1 squared plus 1. This is equal to 2. So this guy here is going to be 2. When we rotate it about y-axis, what we get is something like this. So this is so it is a cylinder. We have taken out a ball from that. So this way the volume is going to be pi. We are going to always have a pi from what bounds of y. So from 1 to 2, the right function is x equal to 1. Well, let me just write like this. This is not nice to write equal in the integrand. I'm just trying to write the right one, minus the left one is, while we are trying to do this one here, yes. So this will be y is equal to x squared plus 1. But we know that x squared plus 1, we have to write everything in terms of y. Well, you solve this for x, you see that x is going to be root y minus 1. Well, you can say plus minus, but here we're only taking the positive values of x. So this will be root of y minus 1 squared. So let me switch this to 1, then dy. This is pi 1 to 2, 1 minus y plus 1. So it will be 2 minus y dy. And that is equal to pi. Antiderivative 2y minus y squared over 2. You go from 1 to 2. And this will give us 4 minus 1 over 2. 4 minus 4 over 2 minus pi, and this is 2 minus 1 over 2. This will give us 2 pi minus the other one is 3 pi over 2, which will give us pi over 2. So the volume of this object here, obtained by rotating a region between the graphs of two functions about y-axis, is equal to pi over 2. So the Washer method has almost nothing new, but the point that the region that we rotate either about x-axis or y-axis is the region between two curves, two positive curves, or two graphs of positive functions.